Common stage, common gate stage. In common source amplifiers, the source follows input signal is applied to the gate of a MOSFET. It is also possible to apply the signal to the source terminal shown in figure A. A common gate CG stage senses the input at the source and produces the output at the drain. The gate is connected to a DC voltage to establish proper operating conditions. Note that the bias current of M1 flows through the input signal source. Alternatively, as depicted in figure B, M1 can be biased by a constant current source with the signal capacitively coupled to the circuit. Here you can see the figure A, common gate stage with direct coupling at input. B, CS stage with capacitive coupling at input. Here you can see the figure A, common gate stage with direct coupling at input. B, CG stage with capacitive coupling at input. We first study the large signal behavior of the circuit in figure A. For simplicity, let us assume that Vin describes that Vn decreases from a large positive value. For Vn greater than or equal to Vb minus Vth, M1 is off, and Vout equal to Vdd for lower values of Vn. We can write Id equal to 1 by 2 nu n C naught x W by L Vb minus Vn minus Vth whole square. If M1 is in saturation as Vn decreases, so does Vout, eventually driving M1 into the triode region. If Vdd minus 1 by 2 nu and C naught x W by L Vb minus Vn minus Vth whole square Rd into Rd is equals to Vb minus Vth. The input output characteristic is shown in figure. If M1 is saturated, we can express the output voltage as Vout equal to Vdd minus 1 by 2 nu and C naught x W by L Vb minus Vn minus Vth whole square into Rd. Here you can see the figure common gate input output characteristic. Obtaining a small signal gate of dou Vout by dou Vn is equal to minus nu n C naught x W by L Vb minus Vn minus Vth into minus 1 in minus dou Vth by dou Vn into Rd. Since dou Vth by dou Vn is equals to dou Vth by dou Vsb is equals to neta, we have dou Vout by dou Vn is equal to nu n C naught x W by L Rd into Vb minus Vn minus Vth into 1 plus neta is equal to Gm into 1 plus neta Rd. Note that the gain is positive. Interestingly, body effect increases the equivalent transconductance of the stage. The input impedance of the circuit is also important. Note that for lambda equals 0, the impedance seen at the source of M1 in figure A is the same as that at the source of M1 in figure, namely 1 by Gm plus Gmb is equal to 1 by Gm into 1 plus neta. Thus the body effect decreases the input impedance of the common gate stage. The relatively low input impedance of the common gate stage proves useful in some applications. Here you can see the figure. The key point in this example is that the overall voltage gain in both arrangements equals minus Gm1 Rd. The value of Rd in figure B can be much greater than 50 ohms without introducing reflections at point X. Thus, the common gate circuit can provide a much higher voltage gain than that in figure A. Now let us study the common topology. Now let us study the common gate topology in a more general case, taking into account both the output impedance of the transistor and the impedance of the signal source depicted in figure A. The circuit can be analyzed with the aid of its equivalent shown. Figure A, CG stage with a CG stage with finite output resistance B, small signal equivalent circuit. In figure B, nothing that the current flowing through RS is equal to minus V out by RD. We have V1 minus V out by RD into RS plus Vin equal to 0. Plus Vin is equals to 0. Moreover, since the rent through R0 is equals to minus V out by RD minus Gm V1 minus Gmb V1, we can write R0 into minus V out by RD minus Gm V1 minus Gmb V1 minus R out by RD into Rs plus V is equals to R out. Upon substitution for V1 from equation reduces to R0 into minus V out by RD minus Gm plus Gmb into V out into Rs by RD minus Vin minus V out Rs by RD plus Vin is equal to V out. It follows that V out by Vin equal to Gm plus Gmb R0 plus 1 by R0 plus Gm plus Gmb R0 Rs plus Rd into Rd. Note that similarly between equation and equation the gain of the common gate stage is slightly higher due to body effect. And the equivalent Thevenin resistance is R equivalent to R0 once in parallel to 1 by Gm B1 parallel to 1 by Gm 1. Redrawing the circuit in figure C, we use equation to write V out by Vin is equals to Gm2 plus Gmb2 R02 plus 1 by R02 plus 1 plus Gm2 plus Gmb2 into R02 into R01 parallel to 1 by Gmb1 parallel to Gm1 plus Rd into Rd R01 parallel to 1 by Gmb1 by R01 parallel to 1 by Gmb1 plus Gm2. The input and output impedances of the common gate topology are also of interest. To obtain the impedance seen at the source, figure A, we use the equivalent circuit in. Here you can see the figure A, input resistance of C, G stage B, small signal equivalent circuit. Figure B, since V1 equal to minus Vx and the gates through R0 is equivalent to Ix plus GMV1 plus GMBV1 is equals to Ix minus GM plus GMB into Vx. We can add up the voltages across R0 plus RD as RD Ix plus R0 into Ix minus GM plus GMB into Vx is equals to Vx. Thus, as Vx by Ix equals to Rd plus R0 by 1 plus Gm plus GMB R0, similar to Rd by Gm plus GMB into R0 plus 1 by Gm plus GMB. If Gm plus GMB into R0 very much greater than 1, this result reveals the drain impedance is divided by Gm plus GMB R0 when seen at the source. This is particularly important in short channel devices because of their low intrinsic gain. Two special cases of equation are worth studying. First, suppose Rd is equal to 0, then Vx by Ix equal to R0 by 1 plus Gm plus GMB R0 is equal to 1 by R0 plus Gm plus GMB, which is simply the impedance seen at the source of a source follower, a predictable result, because if Rd equals 0, the circuit configuration is the same as in figure A. Second, let us replace Rd with an ideal current source equation predicts that the input impedance approaches infinity. While somewhat surprising, this result can be explained with the aid of figure, since the total current through the transistor is fixed and equal to I1. A change in the source potential cannot change the device current. Hence Ix is equals to 0. In other words, the input impedance of a common gate stage is relatively low only if the load impedance connected to the drain is small. Here you can see the figure, input resistance of CG stage with ideal current source load. In order to calculate the output impedance of the common gate stage, we use the circuit here you can see the figure. We note that the result is similar to that in figure, and hence R out equal to 1 plus Gm plus GMB R0 into Rs plus R0 parallel to Rd. Figure calculation of output resistance of a CG stage. Thank you.